Well, welcome to question 2 from chapter 6, the Fundamentals of Particle Technology book, and it's about Thickener Design. And before talking about Thickener Design, I better just quickly recap on what a thickener looks like. This is a fairly basic schematic diagram of a thickener, and by design what we normally mean is that we're looking for the plan area. So if you're looking down on the thickener rather than sideways on, which is what this is an illustration of, then we'd be looking for this area from here to here, the internal surface area from this side to this side, and it is a circular cross-section, circular looking down on it. So it's a diameter, a thickener diameter. A key part to the analysis is this simple flux balance, where F is the feed rate, meters cubed per second, C0 is the inlet concentration on a volume per volume basis, so that means it's dimensionless, it's the volume concentration of the feed going in. Rho S is the solid's density, and if you work out what all these are dimensionally, meters cubed per second, volume for volume, dimensionless, kilograms per meter cubed, that gives you a flux in terms of kilograms per second of material entering the thickener. All those solids, if the thickener is doing its correct job, should end up coming out down here. The same kilograms per second going in should also be coming out down the bottom here, because the thickener underflow, that's what we're talking about down here, the material coming off the bottom of the thickener should have all the solids in it. The thickener overflow, which is just overflowing a weir around the top of the device, is just clean liquid. So if the process is working correctly, we have a feed coming in, goes into the centre, into a feed well, the solids settle down, sediment down, and slowly work their way down, normally with a mechanical rake helping them to the bottom and then being pushed out. Okay, so we're going to certainly talk a lot about a flux balance. In the flux balance, we don't normally bother with the solid's density, because F times C0 will simply be giving us the meters cubed per solid as a volume, and that volume of solids coming in has to be the same as the volume of solids meters cubed per second going out. So essentially it's a material balance, but we'll just use normally a volume balance, because there should be 0 coming out in the overflow, 0 solids coming out in the overflow, everything coming out in the underflow. If we don't provide sufficient area for the thickener, if we make the thickener too small a diameter, then our problem is that this sludge blanket here will rise up, because we're putting too much solids in. For a given feed rate, we're putting too much solids in compared to what the vessel can cope with, so it starts to just fill up, and eventually the solids will come out in the overflow, which is really bad news. Okay, so it's all about designing a continuous process with continuous feed, continuous overflow, and continuous underflow removal from the thickener. And this carries on really from the previous question 1, where we designed a batch tank to do the job of 3% suspension being added, but we discovered that a batch tank wasn't feasible. There's too much solids being added for this 3% by volume solids, and we needed to treat 1,000 meters cubed per day of suspension. They were the 2 key elements for our previous question, and it's just infeasible to actually design a batch tank to do this. Hence we are now designing a continuous thickener to do the job. And one of the elements for the continuous thickener is we have to decide what underflow concentration to use. This particular underflow concentration has been decided upon, and the reason behind that is you have to be able to pump it, so it can't be too concentrated, but at the same time you want it to be the highest concentration possible, because that takes some of the load off the next unit operation, which is invariably a filter, and you want to feed that with a higher concentration as possible, but you still want to be able to readily pump the slurry from the bottom of the thickener. And clearly tests have told us that 13.8% is the safest value to use. Right, now there's a lot of graphical construction in the Flux approach to thickener design, so I'm obviously going to have to use something a little bit more sophisticated than just Microsoft Whiteboard. I'm going to go over to Excel for the rest of the problem. Just to recap here some important details though, the 0.03 volume per volume is what is currently what was used for the batch sedimentation vessel, and what we're going to try and do is to work out what the settling velocity, and therefore the flux, the batch flux, is at these other concentrations at, if we call that 3%, this is 3.9%, that's 4.5%, 4.9%, 5.6%, 6.7%, 7.4% rather, and 9.2%. All, of course, less than the underflow concentration of 13.8%. These are the just a fairly arbitrary collection of concentrations between what we have as the feed, the 3%, and the underflow, 13.8%. So somehow we need to convert our batch settling curve that we had in question 1 into really batch settling curves at these different concentrations, as each one of these different concentrations. That's the first part of the process, because once we've got these settling velocities here, then we can calculate the batch flux quite straightforwardly, as we'll see as we go on. So without any further ado, let's move over to Excel. So just to recap, we're trying to work out the area of the thickener and therefore the diameter of the circular thickener, and then we've also been asked for the underflow rate and the overflow rate. Right, so here is our batch settling curve. This is interface height against time. So this is data from the first question, watching the interface slowly fall down, slowly sediment down, provided this curve here. And we know that whilst we have a constant decline rate just here, the interface has a concentration of 3%. The concentration of solids just under the interface is 3%. When we get to the curved region, we know that the concentration under that interface is higher than 3%, which is the reason why it slows down, which is the reason why we've got this curvature just here until eventually it all settles out at some value. So this is our settling data. We've just plotted it just here, and if the name of the game is all about trying to find a settling concentration, a settling velocity for a certain concentration, we've clearly got that for the 3% value, because it's the gradient of this line, this initial line. But we need more than that. There are all the other volume concentrations that were just highlighted a few moments ago, between 3 and 13.8%. We need an array of values between that feed concentration and the desired underflow concentration. So how do we obtain that from this single batch settling curve? That's essentially what the problem is. Well, we take tangents. A tangent just here is by definition going to be a settling velocity. It's the rate of change of height with time, dv dh dt rather, so that will be a velocity. The key to it though is understanding where to draw the tangent to this curve. How do we work out where to draw the tangent to this curve? And that is what's below, just here. Looks a bit horrible because we've got lots of data. Just to remind you, it starts at 28 centimetres. Okay, so I'll push that off the top of the screen, but we're starting at 28 centimetres. Well, the first piece of data comes from the 3% settling data, 28 centimeters, and the line, the initial settling line, is extended down here. Around about 140 minutes is where it hits the x-axis, so we know they've got a settling velocity of more or less 3.33 times 10 to the minus 5 meters per second. That's that initial settling velocity. Now we could make up suspensions with all these other concentrations and allow them to settle and look for the initial settling velocity, or we could try an alternative technique, which is where we just take these tangents to the settling curve. So in other words, 3.9%. We're using C0 H0 equals C1 H1. It's a material balance. If we multiply area and density on both sides, then that becomes kilograms per second of solids equals kilograms per second of solids. Area and density will cancel out though, so we just need C0 H0 equals C1 H1. And we know that 3, or 0.03, is C0, the original concentration, times by H0, which is 28 centimeters or 0.28 meters, will equal whatever concentration, arbitrary concentration we want, times by some equivalent height. So if we go for 0.039 as our first arbitrary concentration, we can work out what H1 is, and H1 is 21.5. So if you imagine a batch measuring cylinder settling from 28 centimeters with 3% by volume solids in it, that will have the same amount of solids in that measuring cylinder as if we have a 3.9% suspension settling from just 21.5 centimeters to start with. Okay, and that's what you would have here. Here is the settling curve of a batch measuring cylinder starting at 21.5, and it would settle until it gets to just here, and then it carries on the blue curve. The reason behind that is to do with these characteristics, which were discussed in the previous question. The characteristics which are emanating up from the base. The 3.9% characteristic hits the curve at this point just here, and as far as the solids are concerned, thereafter, it doesn't know whether it started at 3.9% solids settling from that height, or 3% solids settling from the 28 centimeter height. It's the same amount of solids at that particular height onwards, regardless of which scenario it started at. And the same logic applies to 4.5%. Again, we can work out what the projected starting height would be. It would be 18.7 centimeters, and that would then settle like that until eventually it became again a tangent to the curve, the original settling curve, and thereafter settling just the same way. And the same is true of all these other settling heights, which have been calculated using this balance down here. So that gives us a whole array of data of settling heights for different concentrations. So we don't need to do lots and lots of batch tests, so long as we have good settling data. We can just take tangents to the settling curve, and by projection work out what the settling velocities are for all these different concentrations. And there's no need to go up to 13.8. You already just have to a substantial amount of concentrations at the lower substantial amount of velocities rather at the lower concentrations. So that should cover us. That should cover us quite nicely there. Okay, so having done that, the next part of the process is to draw the batch flux curve. Batch flux is simply the settling velocity times by the solid's concentration. Now that will have units of meters cubed per second. If you were to multiply by the area, the plan area of the thickener, that would be meters cubed per second. Multiplied by the density, that would be kilograms per second. So hopefully you can see how that ties in with our initial statement on this is all to do with a flux balance based on kilograms per second, meters cubed per second, or if we divide by area and density, just meters per second. So that is our settling velocity. If we multiply by the concentration, that is the batch flux. Okay, so here are the batch fluxes at different solids concentrations, and clearly we want a high batch flux. The higher the batch flux, the better the settling velocity. Now at this stage it's terribly tempting to think that you're going to have to design the thickener for the lowest batch flux, but that's not true, because you have an additional flux inside the thickener due to that underflow withdrawal. It's quite a complicated graphical construction, but the underflow withdrawal induced flux within the thickener adds some more flux, and all you really need to do for the thickener design is to draw a tangent from the desired underflow concentration on the batch flux curve, which is 0.138 on this scale. Draw a tangent and look at the projection of where it hits the batch flux axis, and it hits the batch flux axis here at a value of about 7.2 times 10 to the minus 7 meters per second. Basically what we're saying is any flux is possible below that value. That value that I've just read out is the limiting flux. When the thickener is in balance with what is coming in equal what goes out into the underflow, is at that value. What we can't have is any value above that, because it would be breaching that batch flux curve. This is the flux handling capability, if you like, of material sedimenting. And if you try and get a value from above here, you're asking for too higher settling rate, settling velocity. So that is the limit, and that provides us with what is called TCU. T is the underflow withdrawal velocity inside the thickener, the induced velocity inside the thickener, and Cu is the underflow concentration. So it's this tangent to the batch flux curve that's important. We can't be above the batch flux curve, we can only be smack on the batch flux curve or below it, but below it would be operating at creating a wider thickener, a larger area, which is unnecessary. We want to know what the design is where it just works. Okay, so we get this value of TCU just there, which is 7.2 times 10 to the minus 7 meters per second. Very, very slow really. What about the feed rate? The feed rate to this device is 1,000 meters cubed per day, but that actually corresponds to that value in terms of meters cubed per second. Is that feed concentration, and the thickener plan area results from that, because the area is equal to, I'll come back over to the whiteboard for a demonstration of that. The area that we're talking about just here is equal to what we put into the thickener, FC0, in terms of flux, divided by this critical flux that we've just worked out, TCU. So we get that from our graphical construction on the batch flux curve, and that is what we know what we're putting in. We know that that was 0.03, we know that that was 1,000 meters cubed per day converted to meters cubed per second, and TCU is something that we get from the graph, which we just had a few moments ago. And that's actually really just a mathematical statement of what we've been talking about. All the solids have to go through the underflow. So that's the solids meters cubed per second in the underflow, and that's the solids meters cubed per second going into the thickener. That's what I mean by that T value there is the velocity inside the thickener for all the solids concentrations that exist, because eventually they're going to come out the bottom here. So it's the induced velocity inside the thickener, and all the solids are coming out in the underflow, if it's designed correctly, we have no solids going out into the overflow. So that simple flux balance there gives us the equation which we just used, area equals FC0 over TCU, and we get the TCU as this tangent to the batch settling curve just here. So the area in this case comes out to be 483 meters squared. If we say that's a circle, then pi d squared over 4 is the area of a circle. That enables us to work out that the Thickener diameter is 25 meters, which is a reasonable size thickener. It's not too big. It's a 25 meter diameter tank, circular tank, typically something in the order of 1 to 3 meters in depth. The depth is not so important as the area here. Okay, well, the question does go on to ask about the underflow rate. Well, we can do another flux balance for the underflow rate. As you see just here, here is the flux balance. This is the feed rate times by the feed concentration. That's got to be equal to the underflow withdrawal rate, meters cubed per second, times by the underflow concentration, because all the solids are coming out the bottom. So the underflow concentration was 0.138. The solids flux entering the thickener, that's F times by C0 is that value. So therefore F times by C0 divided by Cu is that, which in terms of some more sensible units is 9.1 meters cubed per hour. So we have 41, just over 41, just under 42 meters cubed per hour going into the thickener, that's the feed, and we have 9.1 meters cubed per hour coming out in the underflow. So the overflow obviously is the difference between whatever we put in, the 42-ish meters cubed per hour going in and the 9.1 meters cubed per hour going out. The balance is actually formally laid out here, but basically what we're saying is that we have let's say 32.6 meters cubed of clean liquid leaving the thickener as the overflow. So in our design, what we have worked out then is the overflow here should be something in the order of 32.6 meters cubed per hour. The underflow was slightly over 9, I think we said it was about 9.1 meters cubed per hour, and that will be at that will be at 13.6 solids, or was it 13.8? I think it was 13.8% actually solids. And the feed that we had going in was at 3% solids. And we can do that all in a thickener which is 25 meters in diameter. That is the minimum diameter. Clearly you'd like to add really a little bit of safety factor to that. You'd probably bring that up to 30 meters in diameter as just to ensure that any fluctuation in the feed rate when it goes up high, you've got the capacity, the hydraulic capacity to cope with that. So you'd go for a significant increase in the diameter as that safety factor. But according to flux theory, which is all covered in chapter 6, that should work with something like 42-ish meters cubed going in, 33 meters cubed of clean liquid being recycled back into the process, and 9-ish meters cubed of suspension at that value going on for further processing. And that is a reasonable sized device, unlike the batch tank that was initially designed based on this settling data. So that is question 2, all about the design of a continuous thickener. Thank you.